send me your presentation, right? And I can share it for everybody.
Oh, okay.
And or you can take a couple more 2 minutes to, I mean, you can still try to figure out what's the problem.
Let's see. I need to get to mail. New window. And this, hit apply, attach. Peru lecture, Congress slides, all slides, Congress PDF, and I send you an email. Did you get my email? Oh, can you hear me?
Yeah, let me check. Let's see if. Yep, I got it. Let me just download it very quickly. Presentación.
Hold shift.
¿Pueden ver que he compartido pantalla?
Sí, sí, se ve, profesor Bertrand.
Oh, share.
What about now, Professor Ball? Can you see your presentation?
I have it on my computer. You can hear me?
Yeah, we can hear you.
So I can look at my slides and tell you when I change. Can you change my slides? No.
Yep. Can you see that? That's the second one, third one.
I don't see them. So now, so start at the title page.
Yeah, I mean, could you just, I mean, don't open your slide, just look at the Zoom page, you know, the Zoom web page.
Yeah, okay. So I can start.
Yeah,
So
just
put the title page up.
Okay, it is there. Can you see that
Did
title
you do
page?
the introduction? Sorry. Okay, so it's a pleasure to be here.
Okay, can you just give me a second? I will make the formal introduction to you.
Oh,
Tengo el placer de presentar al profesor Joe Gold, el profesor emérito de Virginia Tech, reconocida mundial en su área de investigación. Fue también mi profesor en Virginia Tech. Bueno, y el título de su charla de hoy is The Many Disguises of the Jordan Decomposition Theorem in Analysis. Okay, Dr. Ball, you can start.
thank you very much. Thank you for allowing me to speak English. And without further ado, let's proceed to page 2, the general setting ordered vector spaces, which I just learned about recently. There's a whole theory about ordered vector spaces in Rees theory, which I'd like to start with. So, so there's a whole operator theory here, positive operators on a Rees space, which is in parallel with bounded self-adjoint operators on a Hilbert space. And there hasn't been much discussion, communication between the two communities. So maybe we could start something here. So you start with axioms. V is a complex vector space, and it has an involution which should satisfy natural conditions. And X is said to be Hermitian, or otherwise called real, if X equals X star. Anti-Hermitian if X equals minus X star. Then you can always take the average of X and X star to get a Hermitian. And you can take 1 over 2ix minus X star. That's also a Hermitian, actually. So then with this decomposition in the real and imaginary parts, which we're familiar with complex numbers, anything in the space is a linear combination, complex linear combination of two Hermitians. So if we restrict to the real things, those that are self-adjoint, then there's a, we assume V also has a partial order. It's only a partial order, and it's compatible with a vector space structure, which means inequality is invariant under translation. And if lambda is a positive scalar, then multiplication by the scalar should preserve positivity. Page 3. Then let us say V has the Jordan decomposition property. If any Hermitian element can be written as the difference of positive elements. And we say V has the minimal Jordan decomposition property if the Jordan decomposition can be done minimally, which means any other decomposition with primes, X plus prime, X minus prime, has the property that X plus prime has to be bigger than or equal to the X plus, and X minus prime has to be bigger than to the X minus. And then it's easy from the definitions that any such minimal decomposition is unique. And this is what we'll call the abstract Jordan decomposition property. Any X in V is a linear combination of Hermitians, and the Hermitians can be written as the difference of positive. And the general question is, for which ordered vector spaces do we have this Jordan decomposition property, or even better, the minimal Jordan decomposition property? So we'll add more structure to our ordered vector space, namely we call it a Reese space or vector lattice. Ordered vector space is vector lattice. Reese space, if you can take least upper bound of any two elements and greatest lower bound of any two elements, they should exist. So in the first course in advanced calculus, we learned the real number system has this property, but more generally, but there you have a total order. More generally, you take real value functions on any set omega with pointwise ordering. Then it's only a partial order, but it still has this least upper bound of two elements property. Continuous functions on a topological space with pointwise ordering will have this property. And all the LP spaces on a measure space, which we study in analysis, have this order property. It's a Reese space. You can take greatest lower bound, least upper bound of two elements. Then that's all you need. You have the order, partial order with compatibility with the linear structure. You get a minimal Jordan decomposition. Namely, you take X plus to be the supremum of X and 0, and you take X minus to be the supremum of minus X and 0. And then you get the X written as the difference of positive elements. And furthermore, if there's another such decomposition, you get the minimality problem. So that's all you need to see that in a Reese space, you always have this minimal Jordan decomposition property. So what it means is that any X, any other decomposition difference of positives is the special X plus the P, and the special X minus plus the same P. That's the only way you can get something different. And the proof is elementary, but if you're just coming out of advanced calculus and you're working with V equal to real numbers, you get to use trichotomy. Any element of the space is either bigger than 0, equal to 0, or less than 0. So here you don't have that, but you have to work a little harder, and you still get this X plus and X minus difference decomposition. So the corollary is that all these spaces, R omega, C omega, LP omega, have this minimal Jordan decomposition property. I was on page 6, if you're following. So now I'm going to page 7. Another definition, we say it's Dedekind complete if any set S contained in V, such that there exists, there's an upper bound. Yeah. Because there's this is the least upper bound property. Any set bound above has a least upper bound. So if we're in a Reese space, we have this if S is a finite set. So now we ask that S has any cardinality, and we have this. So the terminology Dedekind comes from one, construction of the real numbers. From the rational numbers, you look at what's called Dedekind cuts, and a real number is defined as the least upper bound of the left Dedekind cut, or the greatest lower bound. You just that's how you define a real number: least upper bound of a certain set, or the greatest lower bound of a certain other set. So then, which spaces are Dedekind complete? Well, everything we had before except continuous functions. So the continuous functions are contained in real value functions on the set omega. Omega now is a topological space. So there's a least upper bound. If it's bound above, there's a least upper bound in R omega, but the guy in R omega may not again be continuous. So C omega is a nice space, but it fails to be Dedekind complete with respect to the natural order. Page 8, we suppose we have a norm on the Reese space, as we would have. And did I say a Reese space has an absolute value function? Namely, it's just you take the decomposition as the difference of positive elements, X plus X minus X minus. You define absolute value X, they call it absolute value X, to be X plus plus X minus. That's absolute value of X in a Reese space. Then the norm is compatible if the absolute value X is less than the absolute value Y in the ordering on the vector space implies the norm X less than or equal to norm Y, and that ordering is on the real numbers. And if V is also norm complete, we say it's a, we have a Banach space. So we call it and we have the order structure. We call this combination a Banach lattice. And there's theorem I'll call Roman numeral 1. The norm dual of a norm Reese space is, in fact, the Banach lattice. So you have to do something to prove that, but we don't have time for details. Page 9, mu is a, now we get to the classical Jordan decomposition theorem. Mu is a complex Borel measurable, measure on a measurable, on the Borel sigma algebra, X is a topological space, then we're going to have the measure splits as a real measure plus I times a real measure, and the real and imaginary part are the difference of positive Borel measures. And so the Reese decomposition property holds for the space of complex Borel measures on with topological space X. So we restrict V to space of finite sign measures, the Hermitian objects, then mu bigger than or equal to nu just means mu minus nu is a there are typos on here, is a positive measure, that should be. And then our Jordan decomposition theorem says if you have a finite sign measure, then you can write it as a difference of positive measures. And furthermore, if you take these, you can arrange that you have a minimal, you can arrange it to be minimal. Namely, they have a Han decomposition. U plus is supported on A, U minus is supported on B, and A and B are disjoint. They're unique, determinedly up to sets of measures 0. So we have our minimal Jordan decomposition. This is the classical version Jordan decomposition theorem for measures. So I like to forget what you did in your real analysis course. Here's the highbrow proof. You quote theorem 1. Real valued functions on omega is a normed Reese space, even though in general not that I can complete. The norm dual of real valued continuous functions, should have been an R there, are the space of finite sign Borel measures with total variation norm. Then we quote theorem 1, MR is a Banach lattice, in particular Reese space, so it has any positive thing is any measure, sign measure is a difference of positive measures, and you just use the Reese property to write down what mu plus is and mu minus is, and you're finished. So it's a soft proof of Jordan decomposition theorem for a Stein measure if you believe theorem 1. So inside theorem 1 is whatever you did in real analysis to get this result. Page 11. More ordered vector space, also known, ordered vector space, also known as vector lattice. So V is, I like to write L of H, bounded linear operators on the Hilbert space. Then we take the self-adjoint operators, and then you can always decompose the general guy as a complex linear combination of self-adjoint guys. And so let's say the real things in L of H are the self-adjoint operators. And the ordering is the Lubner ordering, which means against any vector x and h, the inner product Sx against x is bigger than or equal to 0. Then this ordering, if you know what it means to be bigger than or equal to 0, you know what it means to be bigger than or equal to anything else. S bigger than or equal to t just means S minus t bigger than or equal to 0. And so you can check self-adjoint operators on Hilbert space from a vector lattice with this Lubner ordering. And by spectral theory, if you have a functional analysis, everybody knows the spectral theorem, then it's easy to see there is a least upper bound for S and 0. Namely, you take the spectral measure for the interval the positive half line, that's a projection. You hit that on S, and that's going to be the least upper bound under this ordering of S and 0. Oops. Oh, yeah. I lost my page. I went, what page am I on?
You're in the page that says more order vector spaces equal vector lattices. Where V equals the space
you have a
of
number?
linear operators.
Oh, that's, oh.
The page starts at V equals B of H, which is the bounded linear operators on Hilbert space H.
So I scrolled higher rather than scrolling lower because I didn't understand what the up and down arrows meant. More ordered vector spaces. Then the next slide is a special case when the Hilbert space H is finite dimensional. Then operators are identified with matrices. And now we're in a sophomore linear algebra course, and we talk about Hermitian matrices. And in the course, you suppress the fact to the students that this is really an operator on a finite dimensional Hilbert space. And the matrix being positive means, again, the inner product, but now we're in a Cn, is positive, the quadratic form against any vector x. And then we have finite dimensional spectral theory for Hermitian matrices that, well, if we take the real, this is a complexification, and n by n matrices over real numbers is a respace with this so-called Loebner ordering. So we have minimal Jordan decomposition theorem holding for Hermitian matrices. Then I like to do the modest generalization where the matrix entries, instead of being complex numbers, are operators on some auxiliary Hilbert space Y. And instead of AJI bar, we take the adjoint of AJI. And we take n by n matrices over linear operators on Y. That can be identified with just linear operators on direct sum of n copies of Y. And we talk about self-adjoint block matrices with entries in L of Y. Then it's not much work to see that with the Loebner ordering on self-adjoint block matrices, this block matrix setup is also a respace. And now I go to the next slide, another generalization of the special case is kernel functions. So now to blow your head open a little more, suppose K is what I'm calling an Ehrenstein kernel, but operator value on a set omega. It just means it has values in the space of operators on the Hilbert space Y, but its domain is Cartesian product omega cross omega instead of just omega by itself. So I want to point out that if omega is just the first n integers, 1, 2 up to capital N, and we say K at the value ij is the matrix with index, row index I, column index j, then this is just what we had before. You have a function on a Cartesian product set, and you assign an operator for each point in the Cartesian product set. And I want to have operators, so the value of aij is a operator on L of Y. Then we define the involution star as the block adjoint. So the value at ZW of the conjugate kernel is the adjoint of the operator at KWZ. Then this is K star is another kernel function. It's an involution. We'll say K is Hermitian if K equals K star. And we'll say K is positive if this condition holds, which is just how you write that the matrix Aij, the block matrix Aij, when you run over any finitely many points, where you write Zij instead of Ij, is a positive operator in the Lubner ordering. But now, omega is possibly infinite. Omega could be uncountably infinite, but all this still makes sense. So it's just a natural generalization of a finite matrix, namely, you only look at finite matrices to define this, but it's an arbitrary finite subset of your set omega. Next page, kernel functions operator theory point of view. So I want to think of a kernel as actually an infinite block matrix. Rows and columns are now indexed by this set omega, and the block entries are operators on Y. Then I can think of it as an operator. You have a column over index W, which would be a continuous index, but take a column of Y, the values in the Hilbert space Y, and I map it to a sum over W in the index set, KZWYW, to get the new value of my vector, infinitely many entries, at Z. So I want to introduce notation L finite Y, Y value functions on Y only finite support, L of Y value functions on omega, possibly whatever support, arbitrary non-zero. Then, because the Y you feed in here is only finite support, this sum is finite. So for every Z, a value comes out, but the result could be could have non-zero entries for every Z. So you have a well-defined operator from L finite to L over the set omega. And if the case omega is just 1 to n, finitely many points, then L finite Y and L Y are the same, and these are our Y value functions, and this is just our matrix point of view for an operator. So next page, kernels continued. We're in the realm of operators between locally convex topological vector spaces. You can put topologies and all this stuff, and so we have operators between more exotic spaces instead of between a Hilbert space, so everything's hard. Then the remark is you have a perfectly good respace here. You have the Hermitian kernels. Any kernel decomposes as a complex linear combination of Hermitian kernels, but it's not always possible to decompose. It turns out one can show, there are examples, you take a Hermitian kernel, it's not possible to decompose it as a difference of positive kernels. The construction back in 1964 of Laurent Schwartz and redone by Daniel Alpai a couple decades later. However, if, say, omega is a open set containing zero in the complex plane, a disk in the plane, and K has additional structure, it's holomorphic in the first variable and conjugate holomorphic in the second variable, then indeed you can write it as a difference of two positive kernels. Decomposability does hold. So that shows nice things happen if you introduce more structure. Next page. There's some Indians introduced a more complicated kernel, Bareto bot feature Skida. You have a point set omega, C star algebra A, Hilbert space Y. And now your kernel goes from the Cartesian product of my point set omega, not into L of Y, but there's an additional argument, operators from A to L of Y. So to see what's going to land in L of Y, you have to evaluate K at CW. Then that's still a function of A. So then you have to evaluate that in A, and then you get something in L of Y. And then they introduced the notion of completely positive. If now what we had before, but the A's enter in this additional argument. So there are reasons why they did this. But this is a intermediate version of more complicated things to come. So you test this condition for all Z's and omega, all A's in our C star algebra A, all vectors in our Hilbert space Y. So I hope everybody knows what C star algebra is. It's concretely, it's a subalgebra of operators on the Hilbert space, which is also closed under taking the adjoint. So we can, if we have A in A, and then the Hilbert space adjoint, A star is also in our algebra A. Then these things can be characterized as there is an existence of a state space, X, a Hilbert space, a star representation of this C star algebra A into operators on X, and a function omega to operators from X to Y, so K decomposes in this way. So star representation means it preserves products and it preserves star. I'll have that written later, actually. Then there are all kinds of connections. The next slide, decomposability for BBLS kernels. If K is a BBLS kernel and the algebra, C star algebra is trivial, meaning complex numbers, then everything's determined by the value of the kernel when you plug in 1 for your complex number. Then what you get is an Ehrenstein kernel. Conversely, if you have a Ehrenstein kernel, then you get a BBLS kernel, but your algebra is just complex numbers. You just take the C and come out scalar. And we already discussed Ehrenstein kernels. So here there's a notion of, so it's a vector lattice. We have this complicated condition for bigger than or equal to 0, and if that's going to respect translation. So we have this ordered vector space, and so we can talk about having the Reese decomposition problem. So, but Ehrenstein kernel was a special case. So therefore, if omega has infinitely many points, then decomposability can fail, because we already saw this for the special case of Ehrenstein kernels. But it can be shown that decomposability holds if the number of omega is finite. Result only recently, but a Charya Dritchell top. Next slide. Quantized functional analysis. This has become a big industry. So the motivation goes back to C star algebra theory. There, you take a Banach algebra. So there's a norm, and the norm should satisfy certain properties. The norm of the product is the product of the norms. The norm of the adjoint is the same as the norm without the adjoint. And the norm of the product is less than or equal to the product of the norms, things like that. Then if you have a Banach star algebra with the norm satisfying these axioms, then one could show it's isometric anthropomorphic to a concrete C star algebra, which was mentioned earlier, star closed subalgebra of L of H for some H, Hilbert space H. So it's operators on a Hilbert space, subalgebra closed under H. Then people wanted to do this without the star. So there's cases without a star. Suppose it's a unital subalgebra of L of H, but it's not closed under the star. That's called an operator algebra. Suppose it's a linear subspace of L of H. That's all, not closed under product, not closed under adjoint. That's just called concrete operator space. Suppose concrete operator system, just a linear subspace of L of H, contains the identity, typo, closed. Now it's closed under the star, but it's not closed under products. Then the question was how to get an abstract axioms to put on a space, the linear space, has to have a norm, and it has a product, or it has a. Here you don't. Concrete operator space is just a norm. It's a Banach space. Classify abstractly. These are all Banach spaces. Which Banach spaces are actually secretly concrete versions of these objects? And then it was discovered that you have to consider more structure. Namely, you have not only a norm on X, but you have to look at matrices over X. Once the concrete object, it's clear how to set up a norm, sorry for the typo, over on matrices of X. So then you have to consider X and all the matrices over X and norms on them, which should satisfy compatibility conditions. And then one gets a satisfactory classification. So that was are we?
Creo que hay otro en el audio, por favor. Cortar el audio, please. Oh, close.
Everything okay?
Yeah, everything okay. You can continue. Sorry, that was a technical problem.
So now I'm on preliminaries for. So this was by way of motivation for something called non-commutative functions. So the non-commutative function, you have you evaluate not only points on some space where it's defined, but also on matrices over these points. So the setting is V is a vector space, and then the quantization is to look at square matrices of all possible sizes over this vector space. Sometimes non-square sizes. And it's a V as a vector space is a module over complex numbers. So when you take matrices over V, you can multiply by complex matrices using the module structure of V. So n by m, V is left module over ck by n, right module over cn by l for whatever n and l you want as it comes up. So when we do this multiplication, we'll just have the point alpha, point c, point beta. Gets us in a different place. We have the notion of non-commutative envelope. Smallest superset omega closed under direct sums. And if we have another vector space V naught, and omega is a domain, but it's a subset of V non-commutative. And so that's our domain for a non-commutative function. And it takes omega into matrices over this other vector space V naught. Then we say F is a non-commutative function if it's graded. So if you're at level n in the domain, you're at level n in the range. N by n matrix over V in the domain, that's omega n, must map to n by n matrix over V naught. Respects intertwinings. So if you have 2 points of whatever size in omega, and one of level n, one at level m, and you have a n by n scalar matrix, then these products make sense. Suppose they're equal, then the values should respect the same relation. And now you have alpha acting on a matrix over V naught in the range, whereas on the domain side, you had alpha acting on a matrix over V. So it's the same alpha, but it can act on whatever space. And this respects intertwining conditions is the same as respects direct sums and respects similarities take together. So sometimes these are easier to work with. And this had origins in work of Joseph L. Taylor, functional calculus for functions with non-commuting operator arguments, which was hard stuff at the time and still not completely resolved. So to give examples, let's introduce notation FD plus for unit of free monoid on degenerators. And then the elements of FD plus are words in the generator. So a element is a juxtaposition of letters. A equals IN up to I1. Each IJ is one of the letters. And then this is Fraktur Z is the D-tuple of freely non-commuting indeterminates. We have formal monomials. Z to the power A is the product of the Z's in the order given by the word, Fraktur A. And a formal polynomial is a linear combination of formal monomials. And to be a polynomial, we ask that the coefficient P alpha is 0 for all defined many alpha in our unit of free monoid. And then this is a non-commutative function if we introduce substitution. We substitute for Fraktur Z, a capital Z, which is a D-tuple of n by n matrices. And then we evaluate P at Z with this piece of A. Well, piece of A is, let's say, piece of A is scalar. Then we just take piece of A times Z to the power A. Z was a D-tuple of operators on the same Hilbert space H. So we can multiply ZIN up to ZI1 and get another operator on H. That's Z to the non-commutative power A. So this is just a polynomial, but with non-commuting multivariable arguments. Next slide, more examples. Then that example suggests you can go all out with, be brave and go for the coefficients not having finite support and hope that the series converges. So you take a formal power series, plug in your Z, hope that it converges, and where it does converge, take that to be your domain of F. Then this will define a non-commutative function on some set in D-tuples of matrices, square matrices. And there's a theorem, if F is locally bounded, then in fact, F is holomorphic. You can view F as the function of the matrix coordinates of Z, and you'll have a holomorphic function. So locally bounded non-commutative function is an algebraic quantized version of multivariable holomorphic function. And if you have, for example, a nice domain is the space of row contractions, where the row comes from, each entry in the row is an n-by-n matrix, such that Z1, Z1 star plus ZD, ZD star is Luther order strictly less than identity. Okay. Then non-commutative kernel, I want to talk about kernels. You quantize all this. So we again have our point set omega, but now it's contained in this non-commutative, we call it the non-commutative domain of all square matrices over V. And you take A to be a C star algebra. And then I'm going to find a kernel from product, Cartesian product omega omega, where omega is now a non-commutative set. And you have a base set, and you have matrices over that set, into operators A non-commutative, Ly non-commutative, which means you have matrices over A and matrices over L of Y. And then you ask it's graded. It takes, if Z is in omega n, W in omega m, then the result is an operator from the argument is n by n matrices over A to values n by n matrices over L of Y. And it should respect intertwinings. It's the same as the pair of conditions respects direct sums, respects similarities. Next slide, non-commutative kernels continued. So an informal definition, it's closely related to non-commutative functions. It's a non-commutative function in the first argument, and it's a non-commutative function in the second argument after you take the star. So when you take the star, then the W appears in the first argument, and without the star, it's a non-commutative function. Thus, non-commutative function is quantized version of holomorphic function. Non-commutative kernel is quantized version of sesquiholomorphic kernel. And the examples are things like this, and completely positive non-commutative kernels. So it look like BBLS condition, but now the points are these non-commutative points. Then, so we have a notion of positivity for such kernels. So we have a vector, such kernels form a vector lattice, and their positivity condition can be written in other ways. And there's a characterization in terms of Kolmogorov decomposition, which we saw for BBLS kernels. Examples of completely positive non-commutative kernels. We can take special cases. Omega is only omega 1. Then and A equals C, then we're back to Ehrenstein kernels. Omega equals omega 1 is a single point. Then we have what's called completely positive map in operator algebra theory. And Kolmogorov decomposition for K is a famous result in operator algebra theory that completely positive maps have a Stein spring representation. And this is a lot. And suppose omega is only at level 1, viewed as a linearly independent subset of V, then but we still have the A, then our K is a completely positive non-commutative kernel is the same as K is a completely positive kernel in the sense of BBLS. So there are lots of connections, lots of things to understand. You have to spend the semester to understand everything. And then to decide the Jordan decomposition problem for non-commutative kernels, then there's a connection with module maps. So here's our problem. Suppose our point set is only finite, and we have a K, which goes omega cross omega to operators from A and C to L when non-commutative. And it's only a non-commutative kernel. And let's say it's a Hermitian non-commutative kernel. And we want to decide, do we have a Jordan decomposition? So our tool is to stack up the ZIs into a big block diagonal Z0. We can organize it as a big N by big N matrix with block IJ of size Ni by Nj. We can define a map phi K from N0 by N0 matrices over A to blackboard bold L, which is N0 by N0 matrices over L of Y. Namely, you do this. Then you have a map just from our operator algebra, N0 by N0 matrices over the C star algebra A, into operators N0 by N0 matrices over L of Y, which we can also think of as operators on N0 direct sum N0 copies of Y. And we like to translate properties of K, the properties of this map phi K, which has all these points, the interplay of the points hidden in this big point Z0. And so the solution is to let S be this bicommutant of Z0, commutant of Z0 in N0 by N0 matrices. This is a subalgebra of N0 by N0 matrices over C, but in general not a star subalgebra. Then we would like it, we say phi from blackboard bold S, which was defined earlier, to blackboard bold L, to be SS star by module map if alpha p beta star comes out alpha beta star from phi of p. And the theorem is K is a non-commutative kernel if and only if phi K is an SS star by module map. And conversely, phi from N0 by N0 matrices over S, that's blackboard bold S, to L is SS star by module map. Then the non-commutative kernel K is such that it comes from, phi comes from K as phi sub K. Then we have this correspondence. Then this is the tool, theorem continued. Then out of this, we don't have time for details. There's a property called complete spectral factorization property. And there are examples from Analysys, and it holds sometimes, it often doesn't hold. So when you have this condition, then, and your omega is finitely many points, then your non-commutative Hermitian kernel has a, is decomposable. And we can get more definitive results for various special cases. In the case when omega is finitely many points, then you restrict to this special case, and you get decomposability holds for BBLS kernels. You recover the result about a Charlie virtual Todd. When it's infinite, we know it's false anyhow. And the other interesting special case is omega is 1 point. Then if the kernel over a 1 point set collapses to a completely positive map. Then this S, which has to be a C-star algebra, is just complex numbers. So we're cool. Then by this partial result we had before, decomposability holds for completely positive math between C-star algebras, which is the result of Woodstock 1981. So if nothing else, it unifies a bunch of results in the area. And thanks for your attention. And again, I apologize for being late, but I hope you hung on and got something out of it nevertheless. Thank you very much.
Thank you, Dr. Ball, for your interesting talk. Let's see if there's any questions maybe from the audience. ¿Hay alguna pregunta del público? So yeah, it was very interesting talk, and we thank you for your collaboration to this Congress, and well, there was a lot of new material, new mathematics that I had never seen before, but so I have
some you have seen.
I have for many years, for about 5 more years to study to understand it.
There's a lot of stuff out there, yes.
Yeah. All right, so bueno, de parte del comité, tenemos ahí un diploma para el profesor Ball. Muchas gracias una vez más. Thank you, Professor Ball. Once again, we have a certificate for the participation in the conference that we will send it by email to you. Okay. Thank you very much.
Thank you.
Daniel.
This meeting is being recorded.
Topological dynamics, in conformal geometry and core entropy. Bueno, so you can start, Daniel. Welcome.
Thank you. Should I share my screen?
Yeah, yes, please.
Let's see. Have I been made a co-host?
Let me see. Yeah, your co-host.
Okay. Here we go. There we go. All right. Is this working?
Not yet.
Okay, 1 second. Sorry.